Hello and welcome to this peaceful journey. Tonight, we'll slowly explore the hidden world beneath our feet, tracing the slow, majestic movements of tectonic plates and the shaping of oceans and continents, letting each moment guide you into calmness and ease. Imagine the Earth's surface gently folding and stretching over eons, with ancient supercontinents drifting silently across the globe. Feel the quiet rhythm of mantle forces beneath you, the subtle undulations that lift mountains, carve valleys and shift coastlines, as vanished seas whisper their stories, and deep oceans hum a soft, resonant song. If these relaxing sessions bring you comfort, please consider liking, subscribing, or sharing your reflections below. Your support is appreciated and helps others discover this serene space. Don't forget to turn on notifications so you won't miss our future moments together. For now, take a deep breath. Allow your body to soften, let go of tension, and let your mind wander gently. Let's begin. The Earth's continents were not always where they are today. Hundreds of millions of years ago, most of the land masses were fused into the supercontinent Pangea. This enormous expanse stretched across much of the planet, surrounded by a vast global ocean called Panthalassa. The collision and eventual splitting of Pangea set the stage for the formation of modern continents, influencing ocean currents, climate, and the evolution of life. Fossils of similar species found on distant continents, such as South America and Africa, provide evidence of this ancient connection, showing how land and sea have always been intimately linked. Long before Pangea, Earth's land was assembled and broken apart multiple times, forming supercontinents like Rhythmic over 1 billion years ago. Each cycle of assembly and breakup reshaped oceans, altered atmospheric circulation, and created mountain ranges that would influence future climates. Sedimentary rocks on modern continents preserve traces of ancient seas, including deposits of limestone, sandstone, and shale, recording the slow rise and fall of ocean levels over time. These rocks act as a geological diary, capturing interactions between land, water, and life over hundreds of millions of years, revealing a world very different from today's familiar continents and oceans. The Atlantic Ocean is relatively young in geological terms, opening about 200 million years ago during the breakup of Pangea. Seafloor spreading along the mid-Atlantic ridge gradually pushed the Americas westward, separating them from Europe and Africa. The creation of new oceanic crust at the ridge continues today at a rate of a few centimeters per year. This slow expansion not only reshaped coastlines, but also altered global ocean circulation patterns, distributing heat and nutrients across the globe. Over millions of years, these changes influenced climate, marine ecosystems, and the migration of species across continents and oceans alike. The Pacific Ocean is the largest and deepest on Earth, occupying more than 1/3 of the planet's surface. Its current shape is the result of complex tectonic interactions, including subduction, seafloor spreading, and volcanic island formation. The Pacific Plate slowly moves northwest, colliding with surrounding continental plates to create the Ring of Fire, a zone of intense volcanic and seismic activity. Island arcs, deep trenches, and vast underwater mountains are all visible reminders of this constant geological motion. Even the distribution of ocean currents, weather patterns, and marine biodiversity is influenced by the Pacific's shifting plates and the continents that border it. Subduction zones are where one tectonic plate slides beneath another, plunging oceanic crust into the mantle. These zones are responsible for forming mountain ranges, deep ocean trenches, and volcanic island arcs. For example, the Andes in South America and the Japanese archipelago were created by the collision of oceanic and continental plates. As these processes continue, they recycle sediments and minerals from the oceans back into Earth's interior, linking the fate of continents and seas. Over millions of years, subduction shapes coastlines, alters marine ecosystems, and plays a crucial role in Earth's long-term carbon and nutrient cycles, connecting continents and oceans in profound ways. Continental shelves are shallow areas extending from coastlines that serve as hubs of marine life. They were often submerged during periods of high sea level and exposed during ice ages. These shelves accumulate sediments transported by rivers, preserving fossils and chemical signals that record the interaction between land and sea. Over millions of years, shifting continents and changing ocean levels have expanded or contracted these shelves, altering habitats for marine species. The fossilized remains of ancient reefs, mollusks, and early fish in continental shelves reveal the slow interplay between rising mountains, eroding land, and the oceans that surround them. The East African Rift is a modern example of continents slowly tearing apart. As the African plate stretches, valleys and depressions form, some of which are now filled with lakes. Over millions of years, this rifting could allow seawater to enter, creating a new ocean. This process demonstrates that continents are not static. They move, stretch, and reshape the oceans that surround them. The slow creation of a new ocean basin will affect climate, river flow, and biodiversity, illustrating how the motion of land masses directly influences the character and circulation of the Earth's oceans. Ancient inland seas covered large portions of continents. The Western Interior Seaway in North America existed around 100 million years ago, splitting the continent in two and providing a habitat for marine reptiles, ammonites, and early fish. Sedimentary deposits from these seas, including chalk and limestone, preserve the chemical and biological conditions of the time. When these inland seas disappeared, they left behind vast fossil records and sedimentary basins, reminding us that continental interiors can alternately be dry land or marine environments. Such transformations demonstrate the ever-changing interface between land and water over geological time. Rivers act as crucial links between continents and oceans, transporting sediments, minerals, and nutrients across great distances. Over millions of years, rivers carved valleys, shaped deltas, and deposited fertile sediment on continental shelves. These deposits nourished marine ecosystems, influenced ocean chemistry, and preserved fossils that tell stories of life and climate through time. The slow accumulation of sediments also provides evidence of shifting coastlines and continental positions, showing how flowing water connects the geologic histories of both land and sea. Rivers are, in a sense, the veins through which continents nourish the oceans. Hotspot volcanism produces chains of islands that trace tectonic plate motion. The Hawaiian Emperor Chain records the Pacific Plate's slow northwest drift over millions of years. As new islands form over stationary hotspots, older islands erode and sink, leaving submerged seamounts behind. These volcanic chains reveal the dynamic interactions between oceanic crust and mantle plumes and show how islands migrate over time with the movement of surrounding continents and oceans. The creation, erosion, and eventual submergence of these islands provide a living map of Earth's tectonic activity and its influence on marine habitats. The Himalayas continue to rise as India collides with Eurasia, altering river systems and climate patterns that influence distant oceans. Rivers originating in these mountains transport sediments and minerals to seas, affecting the chemical balance of ocean water. The uplifted terrain also redirects atmospheric circulation, impacting monsoon patterns and ocean currents. Over geological time, the Himalayas' growth has influenced the distribution of life on land and in adjacent oceans, showing how the rise of continental mountains can reshape ecosystems and marine environments even thousands of kilometers away. Submerged microcontinents, like the Kerguelen Plateau in the southern Indian Ocean, provide evidence of ancient land masses that were once part of Gondwana. These fragments now lie beneath ocean water, but influence seafloor topography, ocean currents, and marine ecosystems. Studying these submerged lands reveals past continental arrangements, rifting events, and ocean formation. They serve as geological records of tectonic processes that gradually separated supercontinents and shaped today's oceans. Despite being underwater, these features remind us that oceans often conceal the hidden remnants of continents that once stood above the waves. Glacial periods repeatedly exposed and submerged continental shelves, influencing ocean currents and climate. As ice sheets advanced, sea levels dropped, exposing land bridges that connected continents, allowing species migration. When glaciers melted, seas rose, flooding lowlands and reshaping coastlines. These cycles created alternating habitats, redistributed sediments, and modified ocean circulation patterns over millions of years. Fossils and sediment layers preserve the evidence of these transformations, revealing the close relationship between glaciation, continental geography, and the dynamics of oceans in a continually evolving Earth system. The Atlantic Ocean is widening while the Pacific Ocean slowly shrinks, demonstrating the contrasting fates of ocean basins. The Mid-Atlantic Ridge produces new crust, pushing continents apart, while subduction zones in the Pacific consume old crust. These movements influence ocean depth, coastline position, and the flow of currents, which in turn affect climate and marine life. Over tens of millions of years, the gradual reshaping of oceans alters habitats, sedimentation patterns, and nutrient distribution, revealing the slow but persistent influence of tectonics on the global system connecting continents and oceans. The Mediterranean Sea formed from the closure of the Tethys Ocean as Africa collided with Eurasia. Its narrow gateways, islands, and deep basins are products of tectonic compression, sedimentation, and fluctuating sea levels. Fossilized marine organisms in its sediments reveal how changes in water salinity, temperature, and currents were linked to continental collisions. The Mediterranean illustrates the complex interplay of shrinking oceans, rising continents, and ecological adaptation, showing that even relatively small seas carry the history of long-term continental and oceanic evolution. Ocean currents are guided by the arrangement of continents and the shape of ocean basins. As land masses drift and seaways open or close, currents redistribute heat, nutrients, and salinity across the globe. These patterns influence climate, marine productivity, and species migration over geological time. The gradual drift of continents has repeatedly altered the direction and strength of currents, demonstrating the subtle but profound ways that landmasses control the rhythm of oceans and the life they sustain. Volcanic island arcs, such as Japan and the Aleutians, emerge where oceanic plates subduct beneath other plates. Over millions of years, these arcs reshape coastlines, provide new land, and affect ocean circulation. Their formation illustrates how tectonic collisions influence both continental geography and marine environments. As arcs grow, erode, and sometimes collide with continents, they leave a record of geological processes that link land and sea, showing that continents and oceans evolve together in an ongoing slow-motion narrative spanning millions of years. The Canadian Shield preserves some of the oldest continental crust, over 4 billion years old, and bears witness to early Earth history. Its rocks contain evidence of ancient oceans, volcanic activity, and the earliest tectonic processes that shaped continents. Glacial deposits and sedimentary layers record sea level fluctuations and climate changes that affected surrounding oceans. Studying these ancient cratons reveals how the oldest continents evolved alongside oceans, providing a geological record that connects land formation, ocean chemistry, and climate over immense spans of time. Subduction zones recycle water and carbon from oceanic crust into the mantle, feeding volcanic activity that releases gases back into the atmosphere and oceans. This slow process affects the long-term chemical balance of seawater and the evolution of marine life. By transporting sediments, organic material, and minerals from the ocean floor back into Earth's interior, subduction demonstrates the deep connection between tectonic forces, continental evolution, and the ongoing reshaping of oceanic and atmospheric systems over geological time. The breakup of Gondwana reshaped the southern hemisphere's continents and oceans. Africa, South America, Antarctica, India, and Australia slowly drifted apart over millions of years, opening the southern Atlantic and Indian Oceans. As seaways formed, ocean currents shifted, altering climate and the distribution of marine life. Fossil evidence, such as similar plant species on now distant continents, traces these ancient connections. The movement of these landmasses demonstrates how continents and oceans are intrinsically linked, with drifting plates controlling not only geography, but also the chemical, thermal, and biological dynamics of the surrounding seas over vast stretches of geological time. The formation of the Indian Ocean followed the separation of Madagascar, India, and Australia from Gondwana. As the ocean basin widened, currents established patterns that continue to influence climate and monsoon systems today. Deep basins, continental shelves, and submerged plateaus trace the history of rifting and seafloor spreading. Coral reefs and fossil deposits along continental margins preserve the story of changing water chemistry, temperature, and life forms. Over tens of millions of years, the slow movement of these continents has dictated the Indian Ocean's shape, its marine ecosystems, and the sedimentary patterns that tell the story of the interplay between land and sea. The Pacific Plate's constant northwestward motion drives the creation of island arcs, volcanic chains, and deep ocean trenches. Subduction zones surrounding the Pacific form the Ring of Fire, producing earthquakes, volcanoes, and new crust. As the plate moves, older islands erode or submerge, while new volcanoes rise, leaving seamounts beneath the waves. This dynamic cycle not only shapes coastlines, but also influences ocean circulation, nutrient distribution, and marine habitats. The Pacific Ocean's history is written in these geological features, revealing how the slow drift of continents and the recycling of oceanic crust continually redefine both land and sea over millions of years. The Antarctic continent has a profound influence on global oceans. Its massive ice sheets regulate sea levels, while glacial meltwater affects the salinity and circulation of surrounding seas. Subglacial lakes and buried valleys preserve evidence of ancient climates and marine incursions. Over millions of years, the continent has shifted, influencing wind patterns and ocean currents, which in turn affect distant ecosystems. Antarctica's movement and ice dynamics demonstrate the feedback loops connecting continents, climate, and oceans, illustrating how the slow reshaping of land masses can dictate the behavior and chemistry of surrounding waters across geological time. The Mediterranean Sea is a remnant of the ancient Tethys Ocean trapped between Africa and Eurasia. Its narrow connections to the Atlantic, deep basins, and complex islands were shaped by tectonic collision and fluctuating sea levels. Fossilized marine life in its sediments records salinity changes, climate shifts, and the rising of mountain ranges nearby. The Mediterranean illustrates how continental collision and ocean isolation create unique marine environments. Its formation is a snapshot of the long-term interplay between land masses and oceans, demonstrating that even relatively small seas carry evidence of vast geological processes unfolding over millions of years. Glacial cycles repeatedly altered coastlines and continental shelves. During ice ages, sea levels dropped, exposing land bridges and extending continental margins. When glaciers melted, seas rose, flooding lowlands and creating shallow seas that nurtured marine life. These fluctuations redistributed sediments, nutrients, and habitats, leaving fossilized records of the changing connections between continents and oceans. Over millions of years, repeated glacial advances and retreats sculpted coastlines, altered ocean circulation, and influenced both terrestrial and marine species distributions. The rhythmic pattern of glaciation exemplifies the slow, ongoing interplay between climate, continents, and oceans. The Himalayan uplift redirected river systems that feed the Indian Ocean, altering sediment supply and nutrient availability. These rivers carry millions of tons of eroded rock and minerals, which influence ocean chemistry and coastal productivity. Over tens of millions of years, the rising mountains have reshaped monsoon patterns, ocean circulation, and marine ecosystems. The Himalayas' impact illustrates how continental tectonics can indirectly govern the composition, currents, and life of oceans far from the uplift itself. Even subtle changes in river discharge can ripple across entire ocean basins, linking mountains and seas in slow, complex interactions. Submerged continental fragments like the Seychelles and Kerguelen plateaus offer glimpses of ancient supercontinents. Once part of Gondwana, these microcontinents now lie beneath oceans, but affect seafloor topography, local currents, and marine ecosystems. They preserve evidence of rifting, continental breakup, and the birth of new ocean basins. Studying these submerged lands reveals the slow, ongoing rearrangement of continents and the oceans they once bordered. Even underwater, these fragments connect present-day oceans with ancient tectonic events, reminding us that land masses and seas are part of a continuous, evolving system. Rivers and deltas serve as bridges between continents and oceans, transporting sediments, nutrients, and organic matter. These deposits build coastal plains and continental shelves, shaping habitats for marine life. Over millions of years, the continuous flow of rivers has influenced ocean productivity, sediment distribution, and even climate patterns. Sedimentary layers along continental margins record these processes, preserving evidence of changing coastlines, sea levels, and ecosystems. The intricate exchange of materials from land to sea demonstrates the slow but profound influence continents exert on oceans, connecting geological, chemical, and biological cycles in an ongoing planetary rhythm. Hotspot island chains, like the Hawaiian Emperor series, record tectonic plate motion over stationary mantle plumes. As the Pacific Plate drifts northwest, new volcanic islands form while older ones erode or submerge. These islands mark the slow movement of continents relative to oceanic plates, and the underwater seamounts they leave behind preserve a geological history of ocean floor evolution. Hotspot volcanism illustrates how dynamic Earth processes link continents and oceans, creating islands, seafloor features, and unique marine habitats over tens of millions of years. Each eruption adds to the narrative of Earth's ever-changing surface. Subduction zones recycle oceanic crust, transporting water, carbon, and sediments into Earth's mantle. This process generates volcanic activity that releases gases, nutrients, and minerals back into oceans and the atmosphere. Coastal mountain ranges, deep trenches, and volcanic islands are all consequences of subduction, shaping coastlines and marine habitats. Over millions of years, this slow recycling links the continents to the oceans they border, influencing ocean chemistry, biodiversity, and climate. Subduction demonstrates that the fate of land and sea are intertwined, with Earth's internal movements leaving lasting imprints on surface environments and life. The Atlantic Ocean's formation was accompanied by a surge in biodiversity, as new coastlines and shallow seas created habitats. Coral reefs flourished and marine species dispersed into newly formed basins. Seafloor spreading pushed continents apart, establishing new currents and altering climate. Over millions of years, these processes shaped the Atlantic's temperature, salinity, and nutrient distribution, influencing both marine life and continental weather patterns. The expansion of oceans demonstrates the direct connection between continental drift, marine ecosystems, and climate, highlighting the slow but persistent power of Earth's tectonic forces. The breakup of Laurasia, the northern supercontinent, created the North Atlantic and Arctic Oceans. As Europe, North America, and Greenland drifted apart, new seaways formed, redirecting currents and affecting climate. Fossil evidence in sedimentary rocks shows that marine life migrated through these emerging oceans, adapting to changing habitats. Over tens of millions of years, the gradual separation of continents transformed ocean chemistry, currents, and biodiversity. This demonstrates the deep connection between tectonic shifts and oceanic evolution, as even small changes in continental positions can ripple through marine ecosystems. Mountain building, or orogeny, impacts the oceans indirectly by controlling rivers, sediments, and climate. Uplifted ranges like the Andes or Rockies capture rainfall, feed rivers, and transport sediments to seas. These sediments nourish continental shelves and marine ecosystems, while the uplift affects wind patterns and ocean circulation. Over millions of years, mountains reshape coastlines, sediment delivery, and nutrient fluxes into oceans. This process highlights the subtle but pervasive influence of continental landscapes on marine chemistry, habitats, and circulation, linking the evolution of land and sea in an intricate slow-motion narrative. Ancient inland seas, like the Western Interior Seaway, periodically flooded continental interiors, leaving vast sedimentary deposits. These shallow seas preserved marine fossils, recorded sea level fluctuations, and shaped the chemistry of sediments. When the seaway receded, the land was exposed, leaving behind evidence of its former marine life. Such cycles demonstrate how continents and oceans interact over geological time, with inland seas appearing and disappearing in response to tectonics, glaciation, and sea level changes. Fossil and rock records reveal these interactions, showing the continual dance of land, water, and life over millions of years. The Pacific Ocean's depth and size are the result of subduction, seafloor spreading, and volcanic island formation. Deep trenches, submerged ridges, and vast abyssal plains trace the history of plate collisions and spreading. Ocean currents and weather patterns are guided by these structures, influencing climate and marine ecosystems. Over geological time, the Pacific has slowly contracted while the Atlantic expanded, illustrating how tectonic forces shape both ocean basins and continents. These processes affect biodiversity, nutrient distribution, and the very rhythm of life across oceans, connecting the slow movement of land with the dynamics of water. Glacial erosion carved fjords, valleys, and basins across continents, redistributing sediments into oceans. These deposits formed continental shelves, altered coastlines, and influenced marine productivity. Over multiple glacial cycles, these processes reshaped continents and seas repeatedly, leaving fossil and sedimentary evidence of their effects. The interplay of ice, land, and water demonstrates the gradual yet dramatic changes continents and oceans undergo, reminding us that even seemingly static landscapes are part of an ongoing slow-motion planetary transformation. Submerged microcontinents provide hidden evidence of Earth's tectonic past. The Kerguelen Plateau, for example, was once part of Gondwana and now lies beneath the southern Indian Ocean. Its submerged terrain affects currents, sedimentation, and marine habitats. Studying these features allows geologists to reconstruct the formation and breakup of supercontinents and the evolution of oceans. They reveal how the continents we see today are only part of a larger system that includes both visible land and hidden submerged fragments, showing that Earth's continents and oceans are deeply interconnected over geological time. Rivers continually shape the interaction between continents and oceans. They carry sediments, minerals, and organic material from uplands to the sea, creating deltas and nourishing marine ecosystems. Over millions of years, these flows have altered continental margins, influenced ocean chemistry, and provided archives of environmental change. Fossils, sediment layers, and chemical signatures within river-delivered sediments preserve records of continental erosion and oceanic response. Rivers exemplify the persistent exchange between land and sea, demonstrating how slow continual processes connect terrestrial and marine systems over geological timescales. The Arctic Ocean is one of Earth's youngest ocean basins, shaped largely by the movement of surrounding continents. Its shallow shelves and deep basins record the slow opening of the Eurasian Basin and the closing of older seaways over tens of millions of years. Sea ice expansion and contraction, driven by both glacial cycles and continental configuration, have influenced salinity, ocean circulation, and marine habitats. Fossilized remains of ancient marine life preserved in Arctic sediments reveal connections to distant seas. This ocean demonstrates how even cold, ice-covered waters are shaped by the shifting positions of continents and tectonic forces over geological time. The formation of the Caribbean Sea resulted from complex interactions between the North and South American plates and the remnants of Gondwana. Subduction zones created volcanic arcs, while rising land masses formed islands and shallow seas. Ocean currents flowing between these islands influenced sedimentation patterns and marine ecosystems. Fossils in the Caribbean region show migrations of species across emerging seaways. Over millions of years, the interplay of tectonic uplift, seafloor spreading and erosion sculpted the archipelago and surrounding seas, illustrating how continental collisions and rifting can generate new marine environments and reshape the life that inhabits them. The formation of the Red Sea demonstrates how continents can birth oceans. As the Arabian Plate slowly pulls away from Africa, the Rift Valley deepens and may eventually flood with seawater. Over millions of years, this process will create a new ocean basin, complete with coastal shelves, sedimentary deposits, and evolving ecosystems. The Red Sea Rift is a living laboratory for understanding the early stages of ocean formation. Studying its geology reveals how slow continental stretching, volcanic activity, and water infiltration combine to transform terrestrial landscapes into new marine environments, connecting the evolution of land and sea in real time. Sea floors spreading along mid-ocean ridges produces new oceanic crust that pushes continents apart. This slow, continuous process widens oceans, forms underwater mountains, and influences currents and nutrient distribution. Over tens of millions of years, seafloor spreading reshapes ocean basins and adjacent continental margins. Fossilized sediments near ridges revealed changing water chemistry and marine life evolution, capturing the interaction of geological activity and ocean biology. The mid-ocean ridge system illustrates the deep connection between Earth's interior and surface, showing that the movement of continents is intimately tied to the creation and evolution of oceans and the habitats they sustain. Ancient inland seas repeatedly inundated continents, leaving sedimentary layers that record the shifting interface between land and water. The Cretaceous Western Interior Seaway stretched across North America, isolating ecosystems and preserving a rich fossil record of marine reptiles, ammonites, and fish. These deposits provide insight into sea level changes, sedimentation rates, and the connection between continental erosion and marine ecosystems. Over millions of years, the rise and fall of these seas demonstrate how continents are periodically submerged, illustrating the dynamic boundary between terrestrial and marine environments and the long-term co-evolution of land, water, and life. The Amazon River system has shaped South America's coastline and influenced the Atlantic Ocean for millions of years. Sediments transported from the Andes create expansive deltas, enrich ocean water with nutrients, and provide habitats for marine life. The river's slow but continuous discharge demonstrates how continental processes feed into the oceans. Over geological time, shifting tectonic plates, uplifted mountains, and fluctuating sea levels have altered river pathways, sediment load, and coastal topography. The Amazon exemplifies the persistent and subtle connection between continents and oceans, showing that rivers act as vital arteries linking terrestrial landscapes with marine ecosystems across vast temporal scales. Hotspot. Volcanism has produced island chains like Iceland, which sits atop the mid-Atlantic ridge. Here, rising magma forms new land, reshapes coastlines, and influences local currents. Over millions of years, Iceland has grown as the Atlantic spreads, providing a visible record of tectonic activity and the slow drift of continents. The island's volcanic soils support unique ecosystems, while nearby ocean circulation is affected by their presence. Studying these formations illustrates how the creation of islands, driven by mantle plumes and plate motion, links geological processes beneath continents and oceans to the habitats and life that develop above and around them. The Great Barrier Reef developed along the eastern coast of Australia as the continent moved northward. Coral growth was influenced by the continental shelf's shape, ocean currents, and nutrient flows. Over tens of millions of years, reefs expanded, eroded, and adapted to changing sea levels, creating one of the most diverse marine ecosystems on Earth. Fossilized coral and sediment layers preserve evidence of the reef's response to tectonic drift, climate variation, and rising and falling seas. This system highlights how continental position, oceanic currents, and long-term geological change combine to shape ecosystems that span both land-influenced coastal regions and open ocean. The Andes Mountains dramatically influence the Pacific Ocean by controlling rainfall and river flow into the sea. Sediments from these rivers feed coastal shelves, supporting marine ecosystems. Uplifted mountains also alter wind patterns, indirectly affecting ocean currents and nutrient distribution. Over millions of years, the growth of the Andes has transformed continental runoff, ocean productivity, and coastal habitats. These interactions demonstrate the indirect but profound influence of continental tectonics on oceanic systems, showing that the rise of mountains far inland can have far-reaching effects on marine life, water chemistry, and global climate patterns. Submerged continental fragments preserve clues about Earth's ancient geography. The Seychelles microcontinent, once part of Gondwana, now lies beneath the Indian Ocean. Its submerged plateaus influence local currents, sediment accumulation, and marine ecosystems. Geological studies of these features reveal past rifting events, continental separation, and ocean formation. Over millions of years, such microcontinents record the slow drift of land masses and the evolving nature of oceans. Their existence illustrates that much of Earth's tectonic history is hidden beneath the waves, linking present-day ocean topography to the movement and rearrangement of continents across geological time. The East African Rift is an active continental rift that may eventually form a new ocean. Lakes now fill its depressions, providing habitats for unique freshwater and marine life. Magma rises, stretching the crust and creating faults that reshape the landscape. Over millions of years, water from rain and rivers could flood the Rift Valley, connecting it to the sea. This slow process demonstrates the early stages of ocean formation, showing how continents pull apart, how rift valleys evolve into basins, and how terrestrial processes gradually give birth to new marine environments over geological timescales. Glacial activity sculpts continental landscapes and influences oceans by transporting sediments into seas. Ice sheets carve valleys, fjords, and basins, leaving behind moraines that modify coastlines. As glaciers melt, meltwater enters the ocean, affecting salinity and currents. Over repeated glacial cycles, continents and oceans are reshaped, creating alternating habitats and preserving sediments that record environmental change. Fossils in glacial deposits reveals species adaptations to shifting land and water. These interactions exemplify the intertwined evolution of continents, ice, and oceans, highlighting the slow yet dramatic influence of ice-driven processes on Earth's surface and marine systems over millions of years. The Atlantic Ocean is widening while the Pacific shrinks, illustrating how tectonics shapes ocean basins. Mid-Atlantic ridge spreading pushes continents apart, while subduction in the Pacific consumes old crust. These changes alter currents, nutrient distribution, and marine habitats. Fossil and sedimentary records reveal shifts in temperature, salinity, and biodiversity over tens of millions of years. The slow expansion of the Atlantic demonstrates how continental drift and oceanic processes are inseparable, with the positions of landmasses dictating the structure, chemistry, and life of surrounding seas in a continuous geological dialogue. The Caribbean Plates movement created volcanic island arcs and shallow seas, shaping marine ecosystems and ocean currents. Subduction and rifting produced unique islands and seaways that served as migration routes for marine life. Fossil records show how species dispersed across these emerging oceans, adapting to changing habitats. Over millions of years, the Caribbean's tectonic evolution influenced sedimentation, ocean chemistry, and biodiversity. This dynamic region illustrates the continual feedback between continental motion and ocean formation, demonstrating that even relatively small land masses can have outsized impacts on surrounding seas and the life they sustain over geological time. Seafloor spreading produces mid-ocean ridges that rise above abyssal plains, creating underwater mountains and new crust. These ridges influence currents, provide habitats for marine organisms, and gradually push continents apart. Fossil and sedimentary evidence preserves the history of these ridges and their effect on ocean chemistry. Over millions of years, ridges reshape ocean basins, alter coastlines, and affect the distribution of life. This process demonstrates the ongoing interaction between Earth's interior, continental, drift, and the evolution of oceans, linking deep tectonic activity to surface environments in a slow, continuous narrative. Ancient inland seas formed shallow marine habitats across continents, leaving sedimentary layers and fossils that preserve environmental history. Sea level fluctuations periodically submerged and exposed land, creating alternating marine and terrestrial landscapes. These processes affected ocean circulation, nutrient distribution, and climate patterns over millions of years. Fossilized marine organisms reveal how species adapted to changing conditions, while sedimentary strata record continental and oceanic interactions. Such cycles illustrate the dynamic, ever-changing boundary between continents and oceans, showing how slow, incremental changes can leave a lasting impact on Earth's surface and its ecosystems. The Himalayas influence rivers that feed into the Indian Ocean, controlling sediment transport and nutrient flow. These sediments nourish coastal shelves, supporting marine life and influencing ocean chemistry. Uplifted terrain also redirects winds and rainfall, affecting ocean currents. Over tens of millions of years, the Himalayas have shaped both continental landscapes and the adjacent oceans, demonstrating the indirect but significant impact of mountain building on marine environments. The movement of continents and the rise of mountains create a web of connections, linking terrestrial topography to the health and distribution of ocean ecosystems. Volcanic island arcs form at subduction zones, producing islands that reshape coastlines and influence ocean currents. Japan and the Aleutians are examples where tectonic activity creates complex landscapes and new habitats. Over millions of years, these islands can collide with continents, add crust, and modify marine ecosystems. Sedimentary deposits and fossil records capture these processes, showing how ocean and land interact dynamically. Island arc formation highlights the continuous slow-motion reshaping of continents and oceans, emphasizing that tectonics is not isolated to land, but actively sculpts the marine world over geological timescales. Submerged microcontinents like the Kerguelen Plateau provide hidden evidence of ancient Gondwana fragments. Beneath the Indian Ocean, these plateaus affect seafloor topography, local currents, and marine life. Geological studies reveal past rifting, continental drift, and ocean formation events. Over millions of years, such features document the slow evolution of continents and oceans, linking submerged land masses to visible continents. These hidden structures remind us that Earth's tectonic history is preserved not only on land, but also beneath the oceans, connecting the present marine environment to ancient continental processes. The Greenland ice sheet covers nearly the entire island, acting as both a reservoir of fresh water and a sculptor of continental landscapes. Beneath its ice, ancient valleys and fjords reveal past connections to the surrounding Arctic Ocean. Meltwater from glaciers feeds the North Atlantic, influencing currents and global climate patterns. Sediment cores extracted from beneath the ice preserve the history of ocean temperatures, salinity, and marine life. Over millions of years, Greenland's ice and underlying topography have interacted with continental drift and ocean circulation, demonstrating how frozen land masses can control marine environments and global climate over geological timescales. The opening of the South Atlantic Ocean began when South America separated from Africa around 130 million years ago. This rifting formed new oceanic crust and shifted the position of continents, altering currents, climate, and ecosystems. Shallow seas along continental margins became fertile grounds for marine life, while sediments from eroding mountains built extensive continental shelves. Fossils preserved in these deposits trace the migration of species across the widening ocean. Over millions of years, the separation of South America and Africa reshaped both continents and the Atlantic Ocean, illustrating how tectonic motion gradually reconfigures land, sea, and the life that inhabits them. The Amazon basin is not just a river system. It is a living archive of continental and oceanic interactions. Sediments carried from the Andes feed the Atlantic, delivering nutrients and supporting marine ecosystems. Over geological time, shifts in tectonic plates and the rising of mountains altered the river's path, its discharge and sediment load. Fossilized pollen and plant material preserved in river sediments reveal past climates, rainfall patterns, and vegetation. The Amazon exemplifies the slow but persistent connection between continents and oceans, where river flow acts as a conduit linking terrestrial processes with the chemistry, biology, and circulation of adjacent seas. The Antarctic continent's position over the South Pole profoundly influences ocean currents. Cold, dense water formed along its coasts drives the Antarctic circumpolar current, distributing nutrients and regulating global ocean temperatures. Ice shelves extend over the Southern Ocean, shaping marine habitats and affecting sea level. Sediments beneath the ice record the continent's tectonic movement and interactions with surrounding oceans. Over millions of years, Antarctica's drift and glaciation cycles have sculpted ocean circulation patterns, influencing ecosystems worldwide. This demonstrates the intimate connection between continental position, ice dynamics, and ocean processes, highlighting the slow yet global impact of tectonics and climate on Earth's seas. The formation of the Red Sea illustrates early ocean genesis. As the Arabian Plate diverged from Africa, a rift valley formed, gradually deepening and allowing seawater to invade. Over millions of years, volcanic activity, sediment deposition, and shoreline changes created a young ocean with unique currents and habitats. Fossils and rock formations along its margins record the evolving connection between land and water. The Red Sea provides a real-time example of how continental stretching initiates ocean formation, showing that the slow drift of tectonic plates can convert terrestrial rifts into permanent marine environments, reshaping local ecosystems and global ocean circulation over geological time. Subduction zones surrounding the Pacific Ocean create deep trenches and volcanic arcs that influence both continents and seas. The Mariana Trench, the deepest point on Earth, formed as oceanic crust was consumed beneath surrounding plates. Volcanic islands rise along subduction zones, while sediments transported from continents feed nearby oceans. Over millions of years, these processes shape coastlines, ocean chemistry, and marine biodiversity. Subduction demonstrates the continuous recycling of Earth's crust, linking continents and oceans in a slow-motion transformation where geological, chemical, and ecological systems interact over vast timescales, revealing the persistent dynamism of our planet. The Himalayas uplift has redirected rivers toward the Bay of Bengal and Indian Ocean, transporting sediments that nourish continental shelves. Over tens of millions of years, the rising mountains influenced monsoons, sedimentation, and ocean currents, affecting both marine life and climate. Sedimentary layers preserved in deltas record these processes, showing the connection between tectonics and ocean chemistry. The Himalayas illustrate how mountains, though far inland, can dictate coastal ecosystems and marine productivity. This slow interplay highlights the interdependence of continents and oceans, demonstrating that landforms and water bodies evolve together in a continuous geological narrative spanning millions of years. The Mediterranean Sea formed as Africa collided with Eurasia, trapping remnants of the Tethys Ocean. Its narrow gateways, deep basins, and islands are products of tectonic compression, fluctuating sea levels, and sedimentation. Fossils preserved in the Mediterranean revealed changes in salinity, temperature, and biodiversity as land masses shifted. Over millions of years, this sea has served as a laboratory for understanding how continents can isolate water bodies, creating unique ecosystems and altering ocean chemistry. The Mediterranean highlights the delicate balance between tectonics, sea level change, and biological adaptation, showing how continental motion can create enduring marine landscapes. The Caribbean Sea's tectonic evolution created a mosaic of islands and seaways. Subduction and rifting formed volcanic arcs and shallow seas, influencing ocean currents, sedimentation, and marine ecosystems. Fossil evidence shows how species dispersed across emerging basins and adapted to changing conditions. Over tens of millions of years, the slow motion of continental fragments reshaped both land and ocean, creating habitats and nutrient pathways that connect the Caribbean's islands with the broader Atlantic system. This region exemplifies the ongoing feedback between tectonics and ocean formation, revealing the intimate bond between continents, islands, and the seas they shape. Hotspot volcanism produces island chains that mark tectonic plate movement. The Hawaiian Islands formed over a mantle plume, with new islands emerging as older ones eroded or sank beneath the Pacific. These volcanic islands influence ocean currents, provide habitats, and record geological history. Over millions of years, their growth and submergence trace the Pacific Plate's northwestward drift. Hotspot chains illustrate the connection between deep Earth processes, tectonic motion, and the evolution of oceanic landscapes, demonstrating how islands, seafloor topography, and plate movement link continents to surrounding seas in an intricate, long-term narrative. Glacial cycles repeatedly expose and submerge continental shelves. During ice ages, lowered sea levels reveal land bridges connecting continents and altering ocean circulation. As glaciers melt, rising seas flood lowlands, forming shallow seas that nurture marine life. Sedimentary deposits preserve fossils, nutrients, and chemical signatures, revealing the interactions between land and ocean. Over millions of years, glaciation reshaped coastlines, redistributed sediments, and influenced ecosystems both on land and in water. These cycles exemplify the dynamic relationship between continents, climate, and oceans, showing that even slow, incremental changes can profoundly transform planetary systems over geological time. The East African Rift exemplifies continental separation and ocean formation. Lakes occupy depressions in the Rift Valley, while stretching crust and volcanic activity reshape the landscape. Over millions of years, water could flood the rift, creating a new ocean and connecting terrestrial systems to marine environments. This slow process demonstrates the early stages of ocean genesis, where continents pull apart, rift valleys evolve, and new seaways emerge. The East African Rift provides a living example of how tectonic motion, erosion, and water accumulation interact to transform land into ocean, linking continental evolution to marine systems over geological timescales. The Andes Mountains direct river systems that feed into the Pacific, transporting sediments that build continental shelves and nourish marine ecosystems. Uplift affects rainfall, winds, and ocean currents, influencing nutrient distribution and coastal productivity. Over tens of millions of years, these geological processes have shaped both terrestrial and marine environments. Sedimentary deposits record the passage of minerals from mountains to sea, revealing the interconnectedness of landforms and oceans. The Andes exemplify how continental features, though distant from open waters, exert profound influence on ocean chemistry, currents, and biological productivity over geological timescales. Ancient inland seas periodically inundated continents, leaving sedimentary deposits that preserve fossils and environmental history. The Western Interior Seaway in North America split the continent and created shallow marine habitats. When waters receded, exposed land recorded evidence of marine life, sedimentation, and climate conditions. Over millions of years, the repeated advance and retreat of these seas reshaped ecosystems and influenced ocean circulation, demonstrating the intimate link between continental topography, sea level fluctuations, and marine life. Fossil and rock records reveal this continuous dialogue between land and water, illustrating Earth's slow but persistent transformation over geological time. Subduction along the Pacific Rim produces trenches, volcanic arcs, and earthquakes that shape coastlines and marine habitats. The Mariana Trench, Aleutians, and Japan's islands are products of oceanic plates plunging beneath continental crust. Over millions of years, these interactions alter sediment distribution, ocean currents, and coastal ecology. Subduction illustrates how plate tectonics connects continents and oceans in a continuous cycle, recycling crust, influencing climate, and shaping marine environments. The slow motion of plates demonstrates that Earth's internal forces are inseparable from surface landscapes and oceans, showing the enduring bond between tectonics and the evolution of life-sustaining seas. The Canadian Shield preserves ancient continental crust and the earliest evidence of ocean-continent interaction. Over 4 billion years old, these rocks reveal tectonic processes, glaciation, and sediment deposition that shaped early oceans. Sedimentary layers capture fluctuations in sea levels, climate, and the distribution of marine life. Glacial erosion transported sediments to surrounding seas, enriching marine habitats. The shield illustrates how continental stability and erosion influence ocean chemistry, circulation, and ecosystems over vast timescales, providing a window into the long-term connection between the oldest landmasses and Earth's oceans. Rivers link continents to oceans, transporting sediments, nutrients, and organic material. Over millions of years, these flows shape coastal plains, build continental shelves, and nourish marine ecosystems. Fossilized sediments preserve evidence of environmental change, sedimentation, and biological adaptation. Rivers are conduits that connect terrestrial erosion, tectonics, and ocean chemistry, showing how slow, persistent processes link land and sea. This constant exchange highlights the interdependence of continents and oceans, revealing how seemingly small flows of water and sediment influence marine habitats, nutrient distribution, and the chemical composition of seas across geological timescales. Volcanic island arcs form where oceanic plates subduct beneath continental plates, producing chains like the Aleutians and Japan. These islands influence currents, coastal sediments, and marine ecosystems. Over millions of years, arcs may collide with continents, add crust, and reshape coastlines. Fossil and sedimentary records capture these processes, showing how islands evolve, erode, and interact with oceans. Island arc formation demonstrates the persistent reshaping of both land and sea, highlighting the slow-motion interplay between tectonics, ocean chemistry, and ecosystems that unfolds over tens of millions of years. Submerged microcontinents like the Kerguelen Plateau reveal ancient Gondwana fragments beneath the Indian Ocean. These features influence local currents, sedimentation, and marine habitats. Geological studies trace rifting, plate movement, and ocean formation. Over millions of years, these submerged lands record Earth's tectonic evolution and its impact on surrounding seas. The existence of hidden continental fragments shows that oceans conceal the history of land masses, connecting submerged features to the slow, ongoing motion of continents and the marine systems that respond to these movements. The Indian Ocean is shaped by the collision of the Indian subcontinent with Eurasia, which lifted the Himalayas and altered monsoon patterns. Sediments carried from these mountains feed the ocean, creating nutrient-rich coastal zones that support diverse marine life. Over millions of years, tectonic collisions changed ocean circulation, salinity, and temperature, while shifting coastlines influenced habitats. Coral reefs and sediment cores preserve records of these changes, revealing how the slow movement of continents shapes the chemistry, currents, and biology of adjacent oceans. The Indian Ocean demonstrates the intertwined evolution of land and sea across geological time. The formation of the Mediterranean Sea involved the closure of the Tethys Ocean as Africa collided with Europe. Narrow gateways limited water flow, concentrating salinity and shaping unique ecosystems. Over millions of years, tectonics uplifted mountain ranges, altered river flow, and influenced sedimentation patterns along coasts. Fossils in Mediterranean sediments capture species adapting to changing salinity, temperature, and habitat. The sea serves as a snapshot of how continental collisions can trap remnants of oceans, alter marine chemistry, and create biologically distinct environments, illustrating the slow but profound influence of tectonic processes on ocean evolution. The Atlantic Ocean widened as North America separated from Europe, forming new coastlines, shallow seas, and habitats for marine organisms. Seafloor spreading pushed continents apart while redistributing ocean currents and nutrients. Fossil records along continental margins reveal how marine life adapted to expanding basins. Over millions of years, the Atlantic's growth reshaped climate, salinity, and biodiversity, demonstrating that the drift of continents drives ocean evolution. The interplay of tectonics, seafloor spreading, and sedimentation highlights the slow but persistent influence of continental motion on the structure, chemistry, and ecosystems of adjacent oceans, connecting land and sea in continuous transformation. Rivers act as arteries linking continents and oceans, carrying sediments, minerals, and organic matter from uplands to seas. Over geological time, shifting river paths and sediment loads influenced ocean chemistry, nutrient distribution, and coastal ecosystems. Fossilized pollen, plant material, and sediments provide a record of past climates, vegetation, and environmental shifts. Rivers exemplify the persistent connection between terrestrial landscapes and marine habitats, showing how slow, continuous flows shape continental margins and the seas that border them. The interaction of rivers with oceans illustrates the intricate web of processes linking continents and seas over millions of years. The Caribbean Sea formed through the complex motion of the Caribbean Plate and surrounding continental fragments. Subduction and rifting created volcanic islands, shallow seas, and seaways, influencing currents and sedimentation. Over millions of years, marine species dispersed and adapted to emerging habitats. Fossil evidence captures these evolutionary and geological changes. The Caribbean demonstrates how the slow movement of continental fragments reshapes both land and sea, creating unique ecosystems and modifying ocean chemistry. This region illustrates the ongoing feedback between tectonics and marine environments, revealing the enduring impact of continental motion on the life and structure of oceans. Glacial cycles have repeatedly reshaped continents and oceans. Ice sheets carved fjords, valleys, and basins, transporting sediments to the sea. As glaciers melted, sea levels rose, flooding coastal plains and forming shallow seas. Over multiple cycles, these processes influenced ocean salinity, currents, and marine productivity. Fossils preserved in glacial deposits reveal how ecosystems adapted to changing landscapes. The interplay between ice, land, and water demonstrates the slow but dramatic influence of glaciation on Earth's surface, showing that even seemingly static continents and oceans are part of an ongoing millennia-spanning transformation. Hotspot volcanism produces island chains that trace tectonic motion over stationary mantle plumes. The Hawaiian Emperor chain, for instance, records the northwestward drift of the Pacific Plate. New volcanic islands rise while older islands erode or submerge, leaving underwater seamounts. These islands alter ocean currents, provide habitats, and preserve geological history. Over millions of years, hotspot volcanism demonstrates the connection between deep Earth processes, tectonic drift, and oceanic evolution. Islands and seamounts form a chronological map linking plate motion to marine ecosystems, showing how the slow movement of continents and plates continuously reshapes oceans. The East African Rift exemplifies the early stages of ocean formation. As continental crust stretches and thins, lakes fill depressions, and magma rises to create new landscapes. Over millions of years, continued rifting may flood the valley, forming a new ocean basin. Rivers and sediments from surrounding highlands will shape coastal zones and influence marine ecosystems. Studying the East African Rift provides insight into the processes that convert terrestrial landscapes into oceanic environments, revealing how slow tectonic motion, erosion, and water accumulation collaborate to create new seas over geological timescales. Submerged continental fragments like the Kerguelen Plateau offer evidence of ancient supercontinents hidden beneath oceans. These plateaus influence local currents, sedimentation, and marine habitats. Geological studies trace rifting, plate movement, and the evolution of surrounding seas. Over tens of millions of years, these submerged lands provide a record of Earth's tectonic and oceanic history. They demonstrate that oceans are repositories of hidden continental fragments, linking present-day marine systems to the slow, persistent drift and breakup of land masses over geological time, shaping both seafloor topography and ecosystem distribution. The Pacific Ocean's Ring of Fire encircles the basin with subduction zones, trenches, and volcanic arcs. Earthquakes, island formation, and coastal uplift result from the slow recycling of oceanic crust beneath continental plates. Over millions of years, these processes shape coastlines, redistribute sediments, and influence ocean currents. Fossils and sediments record these changes, showing how tectonics, oceans, and life evolve together. The Ring of Fire demonstrates the interconnectedness of continents and oceans, highlighting the persistent geological forces that sculpt coastlines, redistribute nutrients, and sustain marine biodiversity over vast timescales. The formation of the Red Sea provides a real-time glimpse into ocean genesis. As the Arabian Plate diverges from Africa, rift valleys deepen and volcanic activity reshapes the landscape. Seawater gradually inundates these valleys, forming shallow seas and unique habitats. Over millions of years, sediments accumulate along coasts and seafloor basins, preserving fossils that record environmental shifts. The Red Sea illustrates how tectonic motion can transform terrestrial landscapes into new ocean basins, linking continental drift, sedimentation, and marine ecosystems in a slow, continuous narrative of Earth's evolution. The Andes Mountains influence rivers that feed into the Pacific, carrying sediments to continental shelves and enriching marine ecosystems. Mountain uplift affects winds, rainfall, and ocean currents, shaping coastal productivity and nutrient distribution. Over tens of millions of years, tectonics have continuously altered river paths, sediment loads, and coastal zones. Sedimentary records preserve the connection between continental erosion and oceanic chemistry. The Andes exemplify how landforms, though distant from open water, can dictate marine environments, demonstrating the persistent interdependence of continents and oceans across geological timescales. Ancient inland seas, such as the Western Interior Seaway, periodically flooded continents, creating shallow marine habitats and depositing sediments. When waters receded, fossilized organisms preserved evidence of past marine life and environmental conditions. Over millions of years, these cycles shaped ecosystems, redistributed nutrients, and influenced ocean circulation. Sedimentary layers provide a window into the dynamic boundary between land and sea, revealing how slow, repeated changes in continental elevation and sea level interact to shape the evolution of both terrestrial and marine environments across geological time. The Greenland ice sheet controls freshwater input into the North Atlantic, affecting thermohaline circulation. Meltwater influences salinity, nutrient distribution, and marine productivity. Sediments beneath the ice preserve the history of glacial cycles, continental drift, and oceanic interactions. Over millions of years, Greenland's ice dynamics have shaped global currents and ecosystems, linking continental ice sheets to ocean chemistry and climate. This illustrates the profound effect that frozen land masses can exert on distant oceans, emphasizing the interconnected evolution of continents, ice, and marine environments across geological timescales. The Caribbean Plate's motion formed volcanic arcs, shallow seas, and emerging islands. Over millions of years, subduction, rifting, and erosion reshaped coastlines, influenced ocean currents, and created unique marine habitats. Fossil evidence captures species migration and adaptation within these evolving seaways. The Caribbean exemplifies the ongoing feedback between continental motion and ocean formation, demonstrating that the slow movement of land masses reshapes both the chemistry and biodiversity of adjacent seas. This dynamic region illustrates how plate tectonics, sedimentation, and marine ecosystems interact over tens of millions of years, connecting land and sea in continuous transformation. Glacial erosion carved fjords, valleys, and basins across continents, depositing sediments into oceans. These materials built continental shelves, influenced currents, and supported marine life. Repeated glaciations shaped coastlines, sea level, and ocean chemistry, leaving fossil records that capture environmental shifts. Over millions of years, ice has been a powerful agent linking continents and oceans, demonstrating how seemingly static landscapes are in constant slow motion. The interplay of glaciers, land, and water highlights the persistent influence of climate and tectonics on marine ecosystems and the evolution of continental margins. Hotspot islands, such as Iceland, rise where mantle plumes intersect mid-ocean ridges. Volcanic activity reshapes coastlines, forms new habitats, and alters ocean currents. Over tens of millions of years, the creation and erosion of islands record plate motion and seafloor evolution. These formations link deep Earth processes to surface environments, illustrating how tectonics, volcanism, and oceans interact continuously. Islands and surrounding seafloor topography influence marine life, sediment deposition, and ocean chemistry, connecting the slow drift of continents with the development and transformation of marine ecosystems. The East African Rift represents a nascent ocean, where continental stretching creates lakes and volcanic landscapes. Over geological time, continued rifting may allow seawater to flood the basin, forming new marine habitats. Rivers and sediments from nearby highlands will shape future coastal zones. The rift demonstrates the early stages of ocean formation, showing how tectonic motion, erosion, and hydrology gradually transform terrestrial landscapes into marine systems. Studying this active region provides insight into the interconnected evolution of continents and oceans, revealing processes that operate over millions of years to sculpt the Earth's surface. Submerged microcontinents like the Kerguelen Plateau lie hidden beneath the Indian Ocean, preserving evidence of ancient Gondwana fragments. These submerged lands influence local currents, sedimentation, and marine habitats. Geological research traces rifting, continental drift, and ocean formation, revealing the slow evolution of both land masses and seas. The existence of such microcontinents demonstrates that much of Earth's tectonic history is concealed beneath oceans, connecting submerged features to visible continents and showing how oceanic and continental evolution are inseparably linked across geological timescales. The Pacific Ocean's mid-ocean ridges produce new seafloor that slowly pushes continents apart. As magma rises and solidifies, underwater mountains form, influencing currents, nutrient distribution, and marine ecosystems. Fossilized sediments along ridge flanks preserve ancient ocean chemistry and biodiversity. Over millions of years, seafloor spreading reshapes ocean basins, widens continents, and modifies coastal landscapes. This slow process demonstrates the intimate connection between the Earth's interior, tectonic motion, and the evolution of oceans, showing how new crust formation drives the continuous transformation of both land and sea, shaping marine habitats across geological timescales. The formation of the Atlantic Ocean transformed global climate and biodiversity. As North and South America drifted away from Europe and Africa, new coastlines and shallow seas developed. Ocean currents redistributed heat and nutrients, influencing marine life migration and evolution. Fossil records along continental margins reveal adaptations to expanding basins and changing salinity. Over tens of millions of years, the widening Atlantic illustrates how tectonic plate motion governs the evolution of oceans and continents, demonstrating the slow yet profound impact of continental drift on currents, sedimentation, and the distribution of marine species worldwide. Greenland's ice sheets shape ocean circulation by releasing cold, dense meltwater into the North Atlantic. These flows drive the thermohaline conveyor, regulating global climate and nutrient cycles. Sediment cores beneath the ice capture ancient glacial advances, retreats, and interactions with ocean currents. Over millions of years, Greenland's ice dynamics have influenced marine ecosystems far beyond the Arctic, illustrating how continental ice masses can dictate oceanic patterns, chemistry, and biodiversity. The interplay between ice, land, and water highlights the slow but powerful feedbacks connecting continents, oceans, and global climate systems over geological timescales. The Caribbean Plates movement produced volcanic island arcs, shallow seas, and seaways. Subduction and rifting altered coastlines, currents, and sediment deposition. Fossil evidence preserves the migration and adaptation of marine species to these evolving habitats. Over millions of years, the Caribbean illustrates how the slow drift of land masses continually reshapes marine ecosystems, alters ocean chemistry, and influences biodiversity. The region demonstrates the persistent, interconnected evolution of continents and oceans, highlighting the subtle yet profound effects of tectonic motion on the distribution of habitats, nutrients, and life across geological timescales. Glacial erosion sculpts fjords, valleys, and basins, redistributing sediments into oceans. Melting ice raises sea levels, creating shallow seas that support diverse marine ecosystems. Repeated glaciations over millions of years have shaped coastlines, ocean currents, and chemistry. Fossilized deposits preserve evidence of environmental change, species adaptation, and sediment transport. The interplay of glaciers, land, and water demonstrates the slow but persistent influence of ice on both continents and oceans. Glacial cycles reveal how climatic shifts sculpt Earth's surface and affect marine life over tens of thousands to millions of years, linking terrestrial and oceanic systems in continuous transformation. Hotspot volcanism forms islands where mantle plumes intersect tectonic plates. The Hawaiian Emperor Chain records the northwestward drift of the Pacific Plate, with older islands eroding and newer islands emerging. These islands influence currents, sedimentation, and marine habitats while preserving geological history. Over millions of years, hotspot activity demonstrates the connection between deep Earth processes, tectonic motion, and oceanic evolution. Islands, seamounts, and surrounding seafloor topography link the slow drift of continents to the structure and ecology of oceans, showing how geologic forces shape both land and sea across geological time. The East African Rift illustrates the earliest stages of ocean formation. Continental stretching produces lakes and volcanic landscapes, slowly thinning the crust. Over millions of years, the rift may flood, forming a new ocean connected to surrounding seas. Rivers and sediments from adjacent highlands will shape future coastal zones and marine habitats. This ongoing process demonstrates the conversion of terrestrial landscapes into oceanic basins, revealing the interplay of tectonics, erosion, and hydrology in creating new marine environments. The rift serves as a living laboratory of how continents and oceans evolve together over geological time. Submerged microcontinents like the Kerguelen Plateau record ancient Gondwana fragments hidden beneath oceans. These plateaus shape local currents, sedimentation, and marine habitats. Geological studies reveal past rifting, continental drift, and the formation of adjacent seas. Over millions of years, such hidden land masses document the evolution of continents and oceans, highlighting the continuity of tectonic processes. These features remind us that oceans preserve the history of vanished continents, linking submerged crust to current marine ecosystems and demonstrating the slow, persistent influence of tectonics on ocean topography, chemistry, and biodiversity. The Pacific Ocean's Ring of Fire forms a dynamic boundary of subduction zones, trenches, and volcanic arcs. Earthquakes, island formation, and coastal uplift result from the slow recycling of oceanic crust beneath continental plates. Over millions of years, these forces shape coastlines, redistribute sediments, and influence marine habitats. Fossil and sedimentary evidence preserve these changes, demonstrating the interconnection between tectonics, oceans, and life. The Ring of Fire exemplifies the persistent geological forces that continuously sculpt continents and oceans, impacting global currents, sedimentation patterns, and marine ecosystems over vast timescales. The Red Sea demonstrates the early stages of ocean formation as the Arabian Plate diverges from Africa. Rift valleys deepen, volcanic activity reshapes the landscape, and seawater gradually floods the basin. Sediments accumulate along coasts and seafloor, preserving fossils that record environmental change. Over millions of years, the Red Sea illustrates how tectonic stretching transforms terrestrial landscapes into ocean basins. This slow-motion evolution links continental drift, sediment deposition, and marine ecosystems, showing how new seas emerge gradually and how land and water continuously shape one another over geological timescales. The Andes Mountains redirect rivers toward the Pacific, transporting sediments that enrich continental shelves and nourish marine ecosystems. Mountain uplift affects winds, rainfall, and ocean currents, shaping coastal productivity. Over tens of millions of years, tectonics altered river paths, sediment loads, and coastal zones. Sedimentary layers record the connection between continental erosion and ocean chemistry. The Andes exemplify the distant yet profound influence of landforms on oceans, demonstrating how slow geological processes shape marine habitats, nutrient cycles, and ecosystems across vast temporal and spatial scales. Ancient inland seas, such as the Western Interior Seaway, repeatedly submerged continents, creating shallow marine habitats. When waters receded, fossilized marine organisms preserved evidence of past environments and sedimentation patterns. Over millions of years, these cycles shaped ecosystems, redistributed nutrients, and influenced ocean circulation. Sedimentary records reveal the dynamic boundary between land and sea, illustrating how slow changes in continental elevation and sea level interact to shape terrestrial and marine environments across geological time. Greenland's ice sheets control freshwater input into the North Atlantic, influencing thermohaline circulation. Meltwater affects salinity, nutrient distribution, and marine productivity. Sediments beneath the ice preserve ancient glacial advances, retreats, and interactions with ocean currents. Over millions of years, Greenland's ice dynamics have impacted marine ecosystems far beyond the Arctic, showing how continental ice masses dictate oceanic patterns, chemistry, and biodiversity. The interplay of ice, land, and water highlights the slow but powerful feedbacks connecting continents, oceans, and climate systems over geological timescales. The Caribbean Sea formed from tectonic interactions between the Caribbean plate and surrounding landmasses. Subduction and rifting created volcanic islands, shallow seas, and seaways that altered currents and sedimentation. Fossils preserve evidence of species migration and adaptation to evolving habitats. Over millions of years, the Caribbean demonstrates the continuous feedback between continental motion and ocean formation, highlighting how slow tectonic drift reshapes ecosystems, modifies ocean chemistry, and influences biodiversity. The region exemplifies the enduring interdependence of land and sea across geological timescales. Glacial erosion sculpts fjords, valleys, and basins, transporting sediments into oceans that shape continental shelves and marine habitats. Melting ice raises sea levels, creating shallow seas and influencing ocean currents. Repeated glaciations over millions of years have continuously reshaped coastlines, chemistry, and ecosystems. Fossils preserved in glacial deposits reveal environmental shifts and species adaptation. Ice, land, and water interact over geological time, demonstrating the persistent influence of glaciation on both continental landscapes and oceanic systems, highlighting the slow yet dramatic evolution of Earth's surface and marine environments. Hotspot islands like Iceland emerge where mantle plumes intersect mid-ocean ridges. Volcanic activity builds new land, reshapes coastlines, and alters currents. Over tens of millions of years, island creation and erosion record plate motion and seafloor evolution. These formations link deep Earth processes with surface environments, illustrating how tectonics, volcanism, and oceans interact continuously. Islands and surrounding seafloor topography influence marine life, sediment deposition, and ocean chemistry, connecting continental drift with the ongoing transformation of marine ecosystems. The East African Rift represents a nascent ocean in the making. Continental stretching forms lakes, volcanic landscapes, and fault systems. Over millions of years, continued rifting may allow seawater to flood the basin, creating new marine habitats. Rivers and sediments from surrounding highlands will shape future coastlines. The rift provides a living example of how terrestrial landscapes gradually evolve into oceanic basins, revealing the slow interplay of tectonics, erosion, and hydrology in creating marine environments over geological timescales. Submerged microcontinents like the Kerguelen Plateau preserve hidden fragments of Gondwana beneath the Indian Ocean. These features influence currents, sedimentation, and marine habitats. Geological studies reveal past rifting, continental drift, and ocean formation. Over millions of years, these hidden landmasses document the evolution of continents and oceans, highlighting the continuity of tectonic processes. Submerged microcontinents connect Earth's ancient landmasses to present-day marine systems, demonstrating the slow, persistent impact of tectonics on ocean topography, chemistry, and biodiversity. The Antarctic continent anchors the Southern Ocean, generating dense, cold water that drives global thermohaline circulation. Ice shelves extend over the sea, affecting currents, sediment deposition, and marine ecosystems. Sediments beneath the ice capture glacial cycles, tectonic motion, and climate history. Over millions of years, Antarctica's drift and glaciation have influenced ocean currents worldwide, demonstrating the profound connection between continents, ice, and seas. This slow-motion interplay highlights how a seemingly isolated landmass exerts far-reaching control over ocean chemistry, circulation, and ecosystems, revealing the deep interdependence of Earth's physical and biological systems across geological time. The opening of the South Atlantic began as South America drifted from Africa, forming new oceanic crust and shallow seas. River sediments enriched continental margins, creating productive habitats for marine life. Fossil records along the coasts show how species adapted to expanding basins and changing currents. Over tens of millions of years, the widening ocean reshaped climate, salinity, and biodiversity. The Atlantic's growth exemplifies how continental separation drives ocean evolution, connecting tectonic drift, seafloor spreading, sedimentation, and ecosystems in a slow yet persistent transformation of Earth's landscapes and marine environments. The Amazon basin is a living archive of continental ocean interaction. Sediments from the Andes flow into the Atlantic, transporting nutrients that sustain marine ecosystems. Over millions of years, tectonic uplift and river path changes altered discharge, sediment load, and coastal productivity. Fossilized pollen and plant debris preserved in sediments reveal past climates, vegetation shifts, and hydrological cycles. The Amazon exemplifies the connection between terrestrial processes and ocean dynamics, showing how rivers act as conduits between continents and seas. Slow but continuous, this interaction shapes biodiversity, sediment distribution, and the chemistry of adjacent marine environments over geological time. the Mediterranean Sea formed as Africa collided with Europe, leaving remnants of the Tethys Ocean trapped between rising mountains. Narrow gateways controlled water exchange, increasing salinity and creating unique habitats. Over millions of years, sedimentation and tectonics shaped islands, basins, and coastlines, influencing currents and marine life. Fossils preserved in Mediterranean sediments capture species adaptation to fluctuating environmental conditions. The sea demonstrates how continental collisions can isolate oceans, alter chemistry, and create biologically distinct ecosystems. It highlights the persistent influence of tectonics on marine evolution and the intricate link between landforms and adjacent seas over geological timescales. The Caribbean Sea's volcanic island arcs resulted from subduction and rifting along the Caribbean plate. Islands rose and eroded while shallow seas developed, influencing ocean currents and sediment deposition. Fossil evidence records species dispersal and adaptation to new habitats. Over tens of millions of years, tectonic motion reshaped both land and ocean, creating nutrient-rich coastal zones and diverse ecosystems. The Caribbean illustrates the continuous feedback between continental drift and oceanic evolution, demonstrating that slow movements of plates and fragments of land persistently alter marine chemistry, habitats, and biodiversity, revealing the profound interconnection of land and sea over geological time. The Himalayas dramatically redirect rivers into the Bay of Bengal and Indian Ocean, delivering vast sediments that build continental shelves and feed marine ecosystems. Mountain uplift alters wind patterns, rainfall, and ocean currents, shaping coastal productivity. Fossilized sedimentary layers record the long-term transport of minerals from mountains to seas. Over tens of millions of years, the Himalayas exemplify how landforms far from oceans govern sedimentation, nutrient distribution, and ecosystem structure, demonstrating the slow but profound influence of continents on ocean chemistry, habitats, and biodiversity, emphasizing the persistent connection between terrestrial and marine systems. Subduction zones around the Pacific Ocean form trenches, volcanic arcs, and earthquake-prone regions that reshape coastlines and marine habitats. The Mariana Trench, Aleutians, and Japan illustrate oceanic crust diving beneath continental plates, driving sediment redistribution and altering currents. Over millions of years, these processes continuously reshape land and sea, influencing marine biodiversity and chemical cycles. Subduction demonstrates the recycling of Earth's crust and the interdependence of tectonics and oceans. This slow-motion transformation highlights how continental margins and ocean basins evolve together, revealing the persistent influence of geological processes on marine environments across vast timescales. The Canadian Shield preserves ancient continental crust, recording Earth's earliest ocean-continent interactions. Over 4 billion years, tectonic processes, glaciation, and sediment deposition shaped adjacent seas. Fossil-rich sediments reveal past fluctuations in sea level, climate, and marine life. Glacial erosion transported nutrients and sediments into nearby oceans, enriching ecosystems. The shield exemplifies how stable continental regions influence ocean chemistry, circulation, and biodiversity over geological time, highlighting the persistent link between Earth's oldest landmasses and surrounding marine systems, and illustrating how even seemingly inert continents continue to shape oceanic evolution. Rivers serve as conduits connecting continents and oceans, transporting sediments, minerals, and organic matter over geological timescales. Shifting river paths shape continental margins, build deltas, and influence marine habitats. Fossilized pollen, plants, and sediments record climatic changes, vegetation, and sedimentation patterns. Rivers exemplify the slow but continuous exchange between terrestrial landscapes and oceans, showing how persistent flows dictate nutrient distribution, sediment accumulation, and ecosystem development. This interplay highlights the deep interconnection of continents and seas, illustrating that over millions of years, even seemingly small terrestrial processes profoundly shape marine chemistry, currents, and biodiversity. Volcanic island arcs emerge where oceanic plates subduct beneath continents, forming chains such as the Aleutians and Japan. Islands alter currents, redistribute sediments, and provide habitats while preserving geological history. Over millions of years, arcs collide with continents, reshape coastlines, and influence ocean chemistry. Fossil evidence captures species adaptation to these evolving habitats. Island arc formation demonstrates the continuous, slow reshaping of land and sea, emphasizing the intricate interplay between tectonics, oceanic processes, and ecosystems. This process highlights the enduring impact of continental motion on adjacent marine environments over geological timescales. Submerged microcontinents, like the Kerguelen Plateau, lie beneath the Indian Ocean, preserving fragments of ancient supercontinents. These structures affect local currents, sedimentation, and marine habitats. Geological studies reveal rifting, plate motion, and ocean evolution over millions of years. Hidden land masses illustrate that much of Earth's tectonic history lies beneath oceans, linking ancient continents to modern seas. The slow, persistent drift of plates and microcontinents shapes seafloor topography, nutrient distribution, and ecosystems, demonstrating the enduring connection between submerged crust and marine life over geological timescales. The Pacific Ocean's mid-ocean ridges continually produce new seafloor, driving the gradual separation of continents. Rising magma forms underwater mountains, reshaping currents, sedimentation, and habitats. Sediment cores along ridge flanks preserve ancient ocean chemistry and life. Over millions of years, seafloor spreading widens ocean basins, alters climate, and transforms marine ecosystems. This slow geological process links deep Earth activity, plate tectonics, and ocean evolution, showing how new crust drives the persistent reshaping of land, sea, and life across vast timescales. The formation of the Atlantic Ocean altered global climate by creating new currents and coastlines. As North and South America drifted from Europe and Africa, shallow seas and continental margins formed, redistributing heat, nutrients, and species. Fossils reveal adaptations to expanding basins and changing salinity. Over tens of millions of years, the widening Atlantic demonstrates how tectonic plate motion governs the evolution of continents and oceans, influencing currents, sedimentation, and biodiversity in a slow, continuous transformation of Earth's landscapes and marine environments. Greenland's ice sheets influence North Atlantic circulation by releasing dense, cold meltwater. These flows regulate salinity, nutrient transport, and marine productivity. Sediments beneath the ice preserve glacial cycles and interactions with ocean currents. Over millions of years, Greenland's ice has impacted distant marine ecosystems, highlighting the interplay between continental ice, oceans, and climate. The slow, persistent feedback between ice and water demonstrates how continents exert far-reaching influence on marine chemistry, circulation, and biodiversity over geological time. The Caribbean plate's tectonic motion created volcanic arcs, shallow seas, and emerging islands. Subduction and rifting altered currents, sedimentation, and habitats. Fossils record species' dispersal and adaptation to these evolving seaways. Over millions of years, the Caribbean illustrates the continuous feedback between continental motion and ocean formation, showing how plate drift reshapes marine chemistry, biodiversity, and coastal structures. The region exemplifies the persistent interdependence of land and sea, highlighting the slow but profound influence of tectonics on oceanic ecosystems. Glacial erosion shapes fjords, valleys, and basins, redistributing sediments into oceans that build continental shelves. Melting ice raises sea levels, creating shallow seas and influencing currents. Repeated glaciations over millions of years have reshaped coastlines, chemistry, and marine habitats. Fossil deposits preserve environmental shifts and species adaptation. The interplay of ice, land, and water demonstrates the persistent influence of glaciation on continents and oceans, showing how slow climatic and tectonic changes drive the evolution of landscapes and marine ecosystems over geological timescales. Hotspot islands like Iceland emerge at mantle plumes and mid-ocean ridges. Volcanic activity forms new land, reshapes coastlines, and affects currents. Over millions of years, island creation and erosion record plate motion and seafloor evolution. These formations link deep Earth processes with surface environments, illustrating how tectonics and volcanism interact with oceans. Islands and surrounding seafloor topography influence marine life, sedimentation, and ocean chemistry, demonstrating how slow plate movement continuously transforms land and marine ecosystems. The East African Rift represents a nascent ocean forming from continental stretching. Lakes, volcanic landscapes, and fault systems gradually widen. Over millions of years, the rift may flood, creating new marine habitats. Rivers and sediments will shape future coastlines. This process provides a living example of how terrestrial landscapes evolve into ocean basins, showing the interplay of tectonics, erosion, and hydrology in creating marine environments over geological timescales. Submerged microcontinents like the Kerguelen Plateau preserve fragments of Gondwana beneath the Indian Ocean. They influence currents, sedimentation, and marine habitats. Geological studies reveal past rifting, continental drift, and ocean evolution. Over millions of years, these features link ancient continents to present-day seas, demonstrating the slow, persistent impact of tectonics on ocean topography, chemistry, and biodiversity. The Pacific Ocean's mid-ocean ridges generate new seafloor that slowly separates continents. Magma rises, forming underwater mountains that influence currents, sedimentation, and marine habitats. Fossil-rich sediments along ridge flanks preserve ancient ocean chemistry and biodiversity. Over millions of years, seafloor spreading widens ocean basins, alters climate, and reshapes ecosystems. This persistent geological process connects deep Earth dynamics to oceanic evolution, illustrating how new crust formation drives the continuous transformation of land, sea, and life across geological timescales. The opening of the South Atlantic began as South America drifted from Africa, creating new oceanic crust and shallow seas. River sediments enriched continental margins, supporting diverse marine life. Fossils along the coasts reveal adaptations to expanding basins and changing currents. Over tens of millions of years, The widening Atlantic reshaped climate, salinity, and biodiversity. This slow tectonic process exemplifies how continental separation drives ocean evolution, connecting seafloor spreading, sedimentation, and ecosystems in a continuous transformation of Earth's landscapes and marine environments. Antarctica's ice sheets anchor the Southern Ocean, producing dense, cold water that drives thermohaline circulation. Ice shelves extend over the sea, altering currents, sediment deposition, and marine ecosystems. Sediments beneath the ice capture glacial cycles, tectonic motion, and climate history. Over millions of years, Antarctica's position and ice dynamics influenced global ocean currents and marine life. The continent demonstrates how even seemingly isolated landmasses exert far-reaching control over ocean chemistry, circulation, and ecosystems, highlighting the deep interconnection of continents, ice, and oceans across geological timescales. The Amazon basin links continents and oceans by delivering sediments and nutrients from the Andes to the Atlantic. Over millions of years, tectonic uplift and river path changes influenced sediment load, coastal productivity, and marine habitats. Fossilized pollen and plant debris preserve records of past climates, vegetation, and hydrological cycles. Rivers act as conduits between continents and oceans, slowly shaping nutrient distribution, sedimentation, and ecosystems. This interaction illustrates how terrestrial processes dictate marine environments, showing the profound connection between continents, rivers, and oceans over geological time. The Mediterranean Sea is a remnant of the Tethys Ocean, trapped as Africa collided with Europe. Narrow straits control water exchange, increasing salinity and shaping unique ecosystems. Over millions of years, tectonics and sedimentation have created islands, basins, and complex coastlines that influence currents and marine life. Fossils reveal species adapting to fluctuating salinity and climate. The Mediterranean exemplifies how continental collisions isolate seas, alter chemistry, and produce biologically distinct habitats, highlighting the persistent influence of tectonics on ocean evolution and the interconnectedness of land and water. The Caribbean Sea formed from subduction and rifting along the Caribbean plate. Volcanic islands emerged, eroded, and created shallow seas that influenced currents and sedimentation. Fossils reveal species adapting to evolving habitats. Over millions of years, tectonic motion reshaped land and ocean, generating nutrient-rich coastal zones and diverse ecosystems. The Caribbean illustrates the feedback between continental drift and ocean evolution, showing how slow tectonic processes continuously alter marine chemistry, habitats, and biodiversity, highlighting the interdependence of land and sea over geological timescales. Glacial erosion, sculpted fjords, valleys, and basins, transporting sediments into oceans that built continental shelves. Melting ice raised sea levels, forming shallow seas that supported diverse marine life. Repeated glacial cycles over millions of years shaped coastlines, currents, and ocean chemistry. Fossil deposits preserve environmental changes and species adaptation. The interaction of ice, land, and water demonstrates the persistent influence of glaciation on both continents and oceans, showing how slow climatic and tectonic processes drive the evolution of landscapes and marine ecosystems across geological timescales. Hotspot islands like Iceland rise at mantle plumes intersecting mid-ocean ridges. Volcanic activity forms new land, reshapes coastlines, and influences currents. Over millions of years, islands emerge and erode, recording plate motion and seafloor evolution. These formations connect deep Earth processes to surface environments, illustrating the interplay of tectonics, volcanism, and oceans. Islands and surrounding seafloor topography shape marine life, sedimentation, and ocean chemistry, demonstrating how the slow drift of plates continually transforms both land and marine ecosystems over geological time. The East African Rift is a nascent ocean, where continental stretching forms lakes, volcanic landscapes, and fault systems. Over millions of years, continued rifting may flood the basin, creating new marine habitats. Rivers and sediments from adjacent highlands will shape future coastlines. The rift offers a live example of how terrestrial landscapes gradually evolve into oceanic basins, revealing the interplay of tectonics, erosion, and hydrology in creating marine environments over geological timescales, illustrating the slow but continuous connection between continents and seas. Submerged microcontinents like the Kerguelen Plateau preserve fragments of ancient Gondwana beneath the Indian Ocean. These structures influence currents, sedimentation, and marine habitats. Geological studies trace rifting, plate motion, and ocean formation. Over millions of years, hidden landmasses connect ancient continents to modern seas, demonstrating the slow, persistent impact of tectonics on ocean topography, chemistry, and biodiversity. The plateau illustrates how submerged fragments of continents continue to shape marine ecosystems and seafloor evolution over geological timescales. The Pacific Ocean's mid-ocean ridges produce new seafloor that slowly drives continental separation. Rising magma forms underwater mountains, influencing currents, sedimentation, and habitats. Sediment cores preserve ancient ocean chemistry and life. Over millions of years, seafloor spreading widens ocean basins, alters climate, and reshapes ecosystems. This ongoing process links deep Earth dynamics to ocean evolution, showing how new crust formation drives continuous transformation of land, sea, and life across geological timescales. The South Atlantic opened as South America separated from Africa, forming new oceanic crust and shallow seas. River sediments enriched continental margins, supporting marine biodiversity. Fossil evidence records species adaptation to expanding basins and changing currents. Over tens of millions of years, the widening Atlantic reshaped climate, salinity, and ecosystems. This slow tectonic process exemplifies how continental separation drives ocean evolution, connecting seafloor spreading, sedimentation, and marine habitats in a continuous transformative cycle of Earth's landscapes and seas. Antarctica influences the Southern Ocean by generating cold, dense water that drives global thermohaline circulation. Ice shelves extend over the sea, shaping currents, sedimentation, and ecosystems. Sediments beneath the ice preserve glacial cycles, tectonic shifts, and climate history. Over millions of years, Antarctica's position and ice dynamics have shaped ocean currents and marine life worldwide. The continent highlights the profound link between ice, land, and oceans, demonstrating how slow processes control chemistry, circulation, and biodiversity on geological timescales. The Amazon basin delivers sediments from the Andes to the Atlantic, nourishing marine ecosystems and building continental shelves. Over millions of years, tectonic uplift and river shifts influenced sediment load, coastal habitats, and ocean chemistry. Fossilized plant material and pollen preserve past climates and hydrology. Rivers illustrate the continuous terrestrial-to-ocean connection, showing how slow processes govern nutrient distribution, sedimentation, and marine biodiversity. This interplay emphasizes the deep interdependence of continents and oceans across geological timescales. The Mediterranean Sea retains remnants of the Tethys Ocean, trapped as Africa collided with Europe. Narrow straits regulated water exchange, raising salinity and shaping distinct ecosystems. Over millions of years, tectonics created islands, basins, and coastlines that influenced currents and marine life. Fossils reveal species adaptation to changing salinity and environment. The Mediterranean demonstrates how continental collisions can isolate seas, modify chemistry, and produce unique habitats, highlighting the persistent impact of tectonics on ocean evolution and the interconnectedness of land and water. The Caribbean Plate's movement created volcanic arcs and shallow seas, forming islands that influenced currents and sedimentation. Fossil evidence records species dispersal and adaptation. Over millions of years, tectonic drift reshaped land and ocean, creating nutrient-rich zones and diverse ecosystems. The Caribbean illustrates how the slow motion of plates continuously alters marine chemistry, habitats, and biodiversity, showing the interconnected evolution of continents and seas over geological timescales. Glacial erosion sculpted fjords, valleys, and basins, transporting sediments into oceans that formed continental shelves. Melting ice raised sea levels, creating shallow seas and shaping currents. Repeated glacial cycles over millions of years modified coastlines, ocean chemistry, and ecosystems. Fossil deposits preserve environmental shifts and species adaptation. Ice, land, and water interact over geological time, demonstrating glaciation's persistent influence on continents and oceans, revealing how slow climate and tectonic processes drive the evolution of landscapes and marine life. Hotspot islands, such as Iceland, rise at mantle plumes intersecting mid-ocean ridges. Volcanic activity creates land, reshapes coastlines, and influences currents. Over millions of years, islands emerge, erode, and record plate motion. These formations connect deep Earth processes to surface environments, showing how tectonics, volcanism, and oceans interact. Islands and surrounding seafloor topography shape marine habitats, sedimentation, and ocean chemistry, demonstrating the slow but continuous transformation of land and sea over geological time. The East African Rift represents a nascent ocean forming through continental stretching. Lakes, volcanic landscapes, and fault systems widen gradually. Over millions of years, seawater may flood the basin, creating marine habitats. Rivers and sediments will shape future coastlines. The rift exemplifies how terrestrial landscapes slowly evolve into oceanic basins, revealing the interplay of tectonics, erosion, and hydrology in forming marine environments over geological timescales. Submerged microcontinents like the Kerguelen Plateau record ancient Gondwana fragments beneath the Indian Ocean. They influence currents, sedimentation, and habitats. Geological studies trace rifting, drift, and ocean evolution. Over millions of years, these hidden landmasses link ancient continents to modern seas, demonstrating the slow, persistent impact of tectonics on ocean topography, chemistry, and biodiversity. The Pacific Ocean's mid-ocean ridges continuously form new seafloor, slowly pushing continents apart. Rising magma creates underwater mountains, influencing currents, sediment deposition, and marine habitats. Sediment cores preserve ancient ocean chemistry and fossils, capturing life and climate over millions of years. seafloor spreading widens ocean basins, redistributes heat, and shapes ecosystems. This persistent geological process connects deep Earth activity to ocean evolution, illustrating how the birth of new crust drives the ongoing transformation of land, sea, and life across geological timescales. The South Atlantic began opening as South America separated from Africa, forming oceanic crust and shallow seas. Rivers transported sediments to continental margins, enriching habitats for marine life. Fossil evidence shows species adapting to expanding basins and changing currents. Over tens of millions of years, the widening Atlantic reshaped climate, salinity, and biodiversity. The slow tectonic process exemplifies how continental drift drives ocean evolution, linking seafloor spreading, sedimentation, and ecosystems in a continuous transformation of Earth's landscapes and oceans. Antarctica's ice sheets anchor the Southern Ocean, producing dense, cold water that drives global thermohaline circulation. Ice shelves extend over the sea, shaping currents, sedimentation, and marine ecosystems. Sediments beneath preserve glacial cycles, tectonic motion, and climate history. Over millions of years, Antarctica's drift and ice dynamics influenced ocean currents and marine life worldwide. The continent demonstrates how even remote landmasses exert far-reaching control over ocean chemistry, circulation, and ecosystems, highlighting the deep interconnection of continents, ice, and oceans across geological timescales. The Amazon basin delivers sediments and nutrients from the Andes to the Atlantic Ocean, sustaining coastal ecosystems and building continental shelves. Tectonic uplift and river shifts over millions of years influenced sediment load, coastal productivity, and ocean chemistry. Fossils of plants and pollen record past climates and hydrology. Rivers act as conduits linking continents and oceans, shaping nutrient distribution, sedimentation, and ecosystems. This interaction highlights how terrestrial processes dictate marine environments, illustrating the profound connection between continents, rivers, and oceans over geological time. The Mediterranean Sea is a remnant of the Tethys Ocean, trapped as Africa collided with Europe. Narrow straits controlled water exchange, increasing salinity and creating unique ecosystems. Over millions of years, tectonics formed islands, basins, and coastlines, influencing currents and marine life. Fossils reveal species adapting to fluctuating salinity and climate. The Mediterranean demonstrates how continental collisions isolate seas, alter chemistry, and produce biologically distinct habitats, emphasizing the persistent impact of tectonics on ocean evolution and the interconnection of land and water. The Caribbean Sea formed from subduction and rifting along the Caribbean plate. Volcanic islands emerged, eroded, and created shallow seas that influenced currents and sedimentation. Fossils show species adapting to evolving habitats. Over millions of years, tectonic motion reshaped land and ocean, generating nutrient-rich coastal zones and diverse ecosystems. The Caribbean exemplifies the feedback between continental drift and ocean evolution, illustrating how slow tectonic processes continuously alter marine chemistry, habitats, and biodiversity, highlighting the interdependence of land and sea across geological timescales. Glacial erosion carved fjords, valleys, and basins, transporting sediments into oceans that built continental shelves. Melting ice raised sea levels, creating shallow seas and influencing currents. Repeated glacial cycles over millions of years reshaped coastlines, ocean chemistry, and ecosystems. Fossil deposits preserve environmental shifts and species adaptation. The interplay of ice, land, and water demonstrates the persistent influence of glaciation on continents and oceans, showing how slow climate and tectonic processes drive the evolution of landscapes and marine life across geological timescales. Hotspot islands like Iceland rise at mantle plumes intersecting mid-ocean ridges. Volcanic activity forms new land, reshapes coastlines, and affects currents. Over millions of years, islands emerge and erode, recording plate motion and seafloor evolution. These formations connect deep Earth processes to surface environments, illustrating the interplay of tectonics, volcanism, and oceans. Islands and surrounding seafloor topography shape marine life, sedimentation, and ocean chemistry, demonstrating the slow but continuous transformation of land and sea over geological time. The East African Rift represents a nascent ocean forming through continental stretching. Lakes, volcanic landscapes, and fault systems slowly widen. Over millions of years, seawater may flood the basin, creating new marine habitats. Rivers and sediments will shape future coastlines. The rift provides a live example of how terrestrial landscapes gradually evolve into oceanic basins, revealing the interplay of tectonics, erosion, and hydrology informing marine environments over geological timescales. Submerged microcontinents like the Kerguelen Plateau preserve fragments of ancient Gondwana beneath the Indian Ocean. They influence currents, sedimentation, and habitats. Geological studies trace rifting, drift, and ocean evolution. Over millions of years, these hidden landmasses link ancient continents to modern seas, demonstrating the slow, persistent impact of tectonics on ocean topography, chemistry, and biodiversity. The plateau illustrates how submerged fragments of continents continue to shape marine ecosystems and seafloor evolution over geological timescales. The Pacific Ocean's mid-ocean ridges generate new seafloor that slowly separates continents. Rising magma forms underwater mountains, altering currents, sediment deposition, and marine habitats. Sediment cores preserve ancient ocean chemistry and fossils. Over millions of years, seafloor spreading widens basins, redistributes heat, and transforms ecosystems. This ongoing process connects deep Earth dynamics to ocean evolution, showing how new crust drives the continuous transformation of land, sea, and life across geological timescales. The South Atlantic opened as South America drifted from Africa, producing new crust and shallow seas. Rivers transported sediments to continental margins, enriching marine habitats. Fossils reveal species adapting to expanding basins and changing currents. Over tens of millions of years, the widening Atlantic reshaped climate, salinity, and ecosystems. This slow tectonic process demonstrates how continental drift drives ocean evolution, linking seafloor spreading, sedimentation, and ecosystems in a continuous transformation of Earth's landscapes and seas. Antarctica's ice sheets anchor the Southern Ocean, generating dense water that drives thermohaline circulation. Ice shelves extend over the sea, affecting currents, sedimentation, and marine ecosystems. Sediments beneath preserve glacial cycles, tectonic shifts, and climate history. Over millions of years, Antarctica's ice dynamics shaped ocean currents and marine life worldwide. The continent demonstrates how land masses exert far-reaching control over ocean chemistry, circulation, and ecosystems, emphasizing the interconnection of ice, land, and sea across geological timescales. The Amazon basin delivers sediments and nutrients from the Andes to the Atlantic Ocean, building continental shelves and nourishing ecosystems. Tectonic uplift and river changes over millions of years influenced sediment load, coastal productivity, and ocean chemistry. Fossilized plant material and pollen record past climates and hydrology. Rivers illustrate the continuous connection between continents and oceans, shaping nutrient distribution, sedimentation, and biodiversity. This interplay highlights the profound link between terrestrial and marine environments across geological timescales. The Mediterranean Sea retains remnants of the Tethys Ocean, trapped as Africa collided with Europe. Narrow straits controlled water exchange, raising salinity and creating distinct habitats. Over millions of years, tectonics formed islands, basins, and coastlines that influenced currents and marine life. Fossils show species adaptation to changing salinity. The Mediterranean demonstrates how continental collisions isolate seas, modify chemistry, and create unique ecosystems, emphasizing the persistent impact of tectonics on ocean evolution. The Caribbean plate's motion produced volcanic arcs and shallow seas. Islands emerged, influencing currents and sedimentation, while fossils document species adaptation. Over millions of years, tectonic drift reshaped land and ocean, creating nutrient-rich zones and diverse ecosystems. The Caribbean exemplifies the continuous interaction of continents and oceans, highlighting the slow yet profound influence of plate motion on marine chemistry, habitats, and biodiversity over geological timescales. Glacial erosion carved fjords, valleys, and basins, transporting sediments into oceans that formed continental shelves. Melting ice raised sea levels, creating shallow seas and affecting currents. Repeated glaciations over millions of years modified coastlines, chemistry, and ecosystems. Fossil deposits preserve environmental shifts and species adaptation. Ice, land, and water interact over geological time, demonstrating glaciation's persistent influence on both continents and oceans, showing how slow processes shape landscapes and marine life across geological timescales. Hotspot islands, such as Iceland, rise at mantle plumes intersecting mid-ocean ridges. Volcanic activity creates land, reshapes coastlines, and influences currents. Over millions of years, islands emerge, erode, and record plate motion. These formations connect deep earth processes to surface environments, showing how tectonics, volcanism, and oceans interact. Islands and surrounding seafloor topography shape marine habitats, sedimentation, and ocean chemistry, demonstrating the slow but continuous transformation of land and sea. The East African Rift represents an emerging ocean basin. Lakes, volcanic landscapes, and fault systems slowly widen. Over millions of years, the rift may flood, creating marine habitats. Rivers and sediments will shape future coastlines. This evolving rift exemplifies how terrestrial landscapes gradually transition into oceanic basins, revealing the interplay of tectonics, erosion, and hydrology informing marine environments over geological timescales. The Indian Ocean's boundaries are shaped by the collision of the Indian Plate with Asia, uplifting the Himalayas and controlling river discharge into the ocean. Sediments from these rivers build continental shelves, nourishing marine ecosystems and influencing ocean chemistry. Over millions of years, tectonic uplift has regulated nutrient flow, coastal habitats, and sediment deposition. Fossils within deltaic sediments preserve past climates and vegetation, revealing long-term interactions between continents and oceans. This slow, persistent feedback highlights how tectonics, rivers, and sedimentation connect terrestrial landscapes with the chemistry, circulation, and biodiversity of adjacent seas. The Antarctic Circumpolar Current, driven by westerly winds around Antarctica, encircles the Southern Ocean and connects Atlantic, Pacific, and Indian waters. It transports cold, nutrient-rich water that sustains plankton blooms, supporting global marine food webs. Sediment cores reveal climate history and glacial-interglacial cycles, recording Antarctic ice sheet behavior over millions of years. This vast current system illustrates the interplay between continental ice, ocean circulation, and marine ecosystems, showing how slow-moving physical processes shape global oceans, distributing heat, nutrients, and life across vast distances and geological timescales. The Great Barrier Reef along Australia's northeast coast demonstrates how continental shelf formation and sea level changes interact with marine ecosystems. Rising and falling seas over thousands of years exposed reefs to cycles of growth and erosion. Sediment cores record coral adaptation to climate shifts and ocean chemistry changes. Rivers deliver nutrients to the reef system, shaping productivity and biodiversity. The reef exemplifies how continental topography, ocean currents, and biological processes interact over geological timescales, illustrating the persistent influence of continents on nearby ocean chemistry, habitats, and the evolution of ecosystems. The Gulf of Mexico formed through the rifting of North America from South America and Africa, creating shallow seas and salt basins. Sediments from rivers, including the Mississippi, build continental shelves, providing nutrients for marine ecosystems. Fossils reveal species adaptation to changing salinity and sedimentation. Over millions of years, tectonics, river systems, and ocean currents shaped the Gulf's unique habitats. This region highlights the slow but persistent interaction between continental drift, sedimentation, and marine evolution, demonstrating how geological processes create productive seas that connect land and ocean over deep time. The Siberian Traps in northern Russia represent a massive volcanic province that influenced both continental landscapes and ocean chemistry. Lava flows, eruptions, and aerosols altered global climate and oceanic circulation millions of years ago. Volcanic sediments enriched rivers and coastal seas, affecting marine ecosystems and nutrient distribution. Fossil evidence preserves species' responses to environmental stress. This slow interaction between terrestrial volcanism and ocean systems exemplifies how continents and oceans continuously influence each other, showing the persistent and far-reaching effects of geological processes on marine life and chemistry over deep time. The Caribbean Sea's complex tectonic history produced deep trenches, volcanic arcs, and island chains. Subduction zones continuously reshape coastlines, currents, and sediment deposition. Fossils record species dispersal and adaptation to evolving marine habitats. Over millions of years, plate motion created nutrient-rich zones that sustain diverse ecosystems. This slow, continuous feedback between land and ocean illustrates how tectonic activity transforms continental margins, reshapes basins, and regulates marine chemistry and biodiversity, revealing the persistent connection between continents and the oceans they border. The Hudson Bay formed from glacial retreat and post-glacial rebound, reshaping North America's northern coastlines. Meltwater and sediments flowed into adjacent seas, influencing salinity, nutrients, and marine habitats. Fossil and sediment records reveal fluctuating sea levels, ice sheet dynamics, and climate shifts over millions of years. This interaction demonstrates the ongoing influence of glaciation on continental margins and oceans, showing how slow processes of ice melt, erosion, and rebound continually reshape marine environments and coastal ecosystems across geological timescales. The Red Sea emerged as Africa and Arabia drifted apart, forming a rift basin that gradually flooded with seawater. Tectonic stretching produced deep basins and shallow shelves, shaping currents, salinity, and sedimentation patterns. Over millions of years, reefs and marine ecosystems adapted to fluctuating water levels and chemistry. Fossil deposits record environmental changes, species dispersal, and geological evolution. The Red Sea exemplifies the persistent connection between continental rifting, ocean formation, and marine life, highlighting how slow tectonic processes continuously shape ecosystems and water chemistry over geological timescales. The Bering Strait's shallow connection between the Pacific and Arctic Oceans regulates currents, nutrient flows, and marine migrations. Glacial cycles repeatedly opened and closed this passage, altering sea levels and salinity. Sediments and fossils record past connections between continents and oceans, documenting species dispersal and adaptation. Over millions of years, this narrow strait has influenced ocean circulation, climate patterns, and biodiversity, illustrating how subtle changes in continental positioning profoundly affect adjacent seas and ecosystems, emphasizing the long-term interplay of land and water. Submerged continental fragments like Zealandia beneath the southwest Pacific preserve remnants of ancient land masses. Though largely underwater, they influence seafloor topography, currents, and marine habitats. Geological studies trace rifting, drift, and ocean evolution over millions of years. Sediment cores reveal chemical cycles and species adaptation. These hidden fragments demonstrate how submerged continents continue to shape marine ecosystems and seafloor structure, highlighting the slow, persistent effects of tectonics on ocean chemistry, currents, and biodiversity. The Arctic Ocean's ice cover moderates salinity and temperature, influencing global thermohaline circulation. Rivers from Eurasia and North America deliver sediments that nourish continental shelves and coastal ecosystems. Fossils in these sediments preserve climate history, species distribution, and glacial cycles. Over millions of years, Arctic ice and freshwater inputs have shaped ocean currents, nutrient distribution, and marine biodiversity. The slow interplay of ice, land, and sea illustrates the profound connection between continents and oceans, showing how persistent processes govern the evolution of ecosystems over geological timescales. The Bay of Bengal receives immense sediment loads from Himalayan rivers, shaping deltaic systems, coastal habitats, and marine productivity. Sediments record climatic fluctuations, tectonic uplift, and monsoon cycles over millions of years. Nutrient-rich waters support marine biodiversity and influence coastal currents. Fossil evidence preserves the adaptation of species to changing environments. This persistent interaction between continental rivers and oceans exemplifies how terrestrial landscapes dictate sedimentation, nutrient distribution, and ecosystem structure in adjacent seas over geological timescales. The Yellow Sea formed from sea level rise inundating the shallow continental shelf between China and Korea. Sediments from rivers enrich the seabed, supporting extensive fisheries and biodiversity. Over millions of years, fluctuating sea levels and sediment deposition influenced currents, habitats, and species adaptation. Fossil records preserve the region's climatic and ecological history. The Yellow Sea illustrates how continental shelves, rivers, and ocean dynamics interact over geological time, highlighting the slow, persistent influence of land on marine environments. The Gulf of California opened as the Baja California Peninsula separated from mainland Mexico, forming a rift basin filled with seawater. Sedimentation, tectonics, and ocean currents created diverse habitats, supporting unique marine life. Fossil evidence captures species adaptation to fluctuating water levels and environmental conditions. Over millions of years, this rift demonstrates how continental drift generates new ocean basins, shapes currents, and regulates sedimentation, illustrating the persistent link between tectonics, landforms, and marine ecosystems. The Scotia Sea forms a tectonic corridor between South America and Antarctica. Subduction, spreading ridges, and shallow shelves influence currents, nutrient transport, and marine ecosystems. Fossil sediments record species migration and environmental shifts over millions of years. This region exemplifies how slow tectonic movements shape ocean basins, redistribute sediments, and create biologically productive zones, highlighting the persistent interplay between continents, oceans, and ecosystems over geological time. The Okhotsk Sea, bordered by Siberia and Japan, experiences currents influenced by rivers, tides, and seasonal ice. Sediment deposition from rivers builds shelves and nourishes marine life. Fossils record past climate fluctuations, glacial activity, and ocean chemistry. Over millions of years, the interplay of land, rivers, and sea has shaped ecosystems and currents, demonstrating the persistent influence of continental positioning and terrestrial inputs on oceanic environments. The Tasman Sea formed between Australia and Zealandia during continental separation, producing new ocean basins and shallow shelves. Currents and sedimentation patterns evolved over millions of years, influencing nutrient distribution and marine ecosystems. Fossil records preserve species adaptation to changing ocean conditions. The Tasman Sea illustrates the continuous feedback between continental drift, seafloor spreading, and marine habitats, showing the slow, persistent influence of tectonics on ocean chemistry, biodiversity, and coastal structures. The Gulf of Aden opened as Africa and Arabia separated, forming a rift that gradually flooded with seawater. Tectonic stretching and sediment deposition created varied seafloor topography, affecting currents and habitats. Fossils revealed species adaptation to changing salinity and water levels. Over millions of years, the Gulf demonstrates the slow, continuous interaction between continental drift, ocean formation, and marine life, emphasizing the persistent link between tectonics and ecosystems. Submerged continental fragments like the Farallon Plate influenced ocean topography, currents, and sedimentation as they sank beneath North America. Geological studies trace rifting, subduction, and drift, revealing ancient ocean formation and plate interactions. Over millions of years, these hidden fragments shaped nutrient flows, habitats, and biodiversity in adjacent seas, illustrating the persistent impact of tectonics on oceans and marine ecosystems. The Arctic's Beaufort Sea experiences riverine sediment input from North America, forming shallow shelves and influencing currents. Sediment cores record glacial history, species distribution, and climate fluctuations over millions of years. Ice cover regulates salinity and temperature, impacting marine habitats and circulation. This slow interplay of rivers, ice, and ocean demonstrates the enduring connection between continents and seas, showing how persistent terrestrial processes shape marine chemistry, ecosystems, and biodiversity over geological timescales. The Coral Triangle in Southeast Asia spans parts of Indonesia, the Philippines, and Malaysia, forming the most biodiverse marine region on Earth. Over millions of years, tectonic uplift, sea level changes, and ocean currents shaped thousands of islands, shallow seas, and nutrient-rich habitats. Sediment deposition from rivers nourishes coral reefs, sustaining marine ecosystems. Fossilized corals and shells reveal adaptations to fluctuating temperatures, salinity, and currents. This region illustrates how complex interactions between continental topography, tectonics, and oceanic processes drive biodiversity, showing the persistent link between shifting land masses, evolving seas, and the life they sustain over geological timescales. The Hudson Shelf Valley, off the northeastern coast of North America, was carved by glacial meltwater during the last ice age. Sediments transported by these rivers formed deep channels and nutrient-rich continental shelves, supporting diverse marine ecosystems. Fossil evidence preserves species adaptation to changing sea levels, salinity, and sedimentation over thousands of years. These glacially sculpted landscapes illustrate the long-term influence of ice sheets on continental margins and adjacent oceans, showing how erosion, sediment transport, and sea level fluctuations continuously shape marine habitats and chemical cycles over geological and ecological timescales. The Sunda Shelf in Southeast Asia connects many islands during periods of low sea level, forming shallow seas that expand and contract with glacial cycles. Sediments from rivers create fertile marine environments, while ocean currents distribute nutrients and support rich biodiversity. Fossil records reveal the rise and fall of sea levels and the migration of species across these temporary land bridges. This dynamic interaction between continental shelves, rivers, and oceans highlights how slowly changing geological and climatic conditions dictate marine chemistry, habitats, and evolutionary pathways over millions of years. The Scotia Arc, linking South America to the Antarctic Peninsula, was formed by subduction, rifting, and volcanic activity. Deep trenches, volcanic islands, and submerged ridges influence currents, nutrient distribution, and marine life. Fossil sediments record environmental shifts, species migration, and adaptation over millions of years. This geologically active region illustrates how tectonic processes continuously shape ocean basins, redistribute nutrients, and generate productive marine ecosystems, emphasizing the persistent feedback between continents, ocean circulation, and biodiversity across geological timescales. The Persian Gulf's shallow waters formed as Arabia collided with Eurasia, creating a basin flooded by seawater. Sediments from rivers like the Tigris and Euphrates enrich the seabed, shaping coastal habitats and marine ecosystems. Fossils preserve species adapting to high salinity, shallow waters, and fluctuating sea levels. Over millions of years, tectonics, sedimentation, and ocean currents have sculpted this unique marine environment. The Persian Gulf exemplifies how slow geological processes and continental movement govern marine chemistry, habitat formation, and biodiversity, highlighting the enduring connection between land masses and the oceans that surround them. As we conclude our time exploring the world beneath our feet, allow yourself to drift even deeper into calm and relaxation. Feel the peaceful energy of Earth's slow, patient movements surrounding you, your body unwinding, your mind letting go, and your breath flowing naturally. Imagine the quiet force of plate boundaries shifting, oceans circulating, and continents embracing the gentle rhythm of time. Rest here, fully embraced by this safe and serene space. If this moment brought you peace, please consider liking, subscribing, or sharing your thoughts below. Your support helps others find this tranquil corner of calm. Turn on notifications so you can join our next journey. For now, relax fully, release any remaining tension, and let your mind float. Sleep well and good night.